review of titration. So we did a titration already this semester, but we did an redox titration with the permanganate solution. Here we're talking about acid-base titrations. But in a titration in general, you have two solutions. One you know the concentration of, one you don't. And so you add the known solution until you get complete reaction with the unknown solution, then you can figure out what the unknown concentration is. The hard part is knowing when do you get to complete reaction. For pH solution or pH titration, we can monitor that using an indicator such as phenolphthalein, which will change color when there's a shift in the pH, or we can use a pH meter. We'll be doing both of those in the upcoming experiment 18, whatever letter it is. A, I think. So the equivalence point is where the number of moles of acid is stoichiometrically equal to the number of moles of base. Many acid-base reactions have a 1-to-1 stoichiometry, but sometimes it's 2-to-1 or 1-to-2. Now we can calculate the concentration of the unknown solution. Pictures, illustrations. So we often have sodium hydroxide in the burette and an unknown acid solution in the flask, and we start adding hydroxide, and each hydroxide ion will react with one hydrogen ion to form water and neutralize the acid. And when it gets to where they've all been neutralized, and probably at least one extra, the pH is going to change enough that the indicator is going to change color. Phenolphthalein is pink in basic solution and colorless in acid solution. This is what it looks like when you're actually titrating it. As you're getting closer, you'll start to see pink here because locally in this area, it's more basic because you added base and it's not mixed yet. But then when you swirl it, it goes clear again. And the goal is to add some and have it be colorless, colorless, and then add 1 drop or less and have it stay pink. And then you know you're really, really close to the equivalence point. So a titration curve, sometimes called a pH curve, is where we're going to plot the pH of the solution being titrated as a function of the volume of solution being added. So here we're talking about titrating a strong acid like HCl with a strong base like sodium hydroxide. And the titration here, we're looking at 50 milliliters of 0.1 molar HCl, and we're titrating it with 0.1 molar sodium hydroxide. So here it's going up, and now the slope changes from positive to negative. Something changes. Chemo brain. We have an inflection point here, where here it was going up more and more rapidly, and now it's going up less and less rapidly. So that the equivalence point is at the inflection point. The pH is going to change very quickly there. Here, you can add 5 milliliters, 10 milliliters of sodium hydroxide, and the pH doesn't change very much. But here you could add 1 milliliter and have the pH jump several units. The exact shape of this is going to depend on several factors, like is it a monoprotic acid or a diprotic acid? Is it a strong acid with a weak base or a weak base with a strong acid? All kinds of different things. We worked with millimoles a little bit at the beginning of the semester, and here's your official introduction to millimoles. Dang it, I forgot millimole again. I have a mole, and I have a small one, right? So she's the millimole, right? I'm supposed to bring them, and I forgot. I forgot yesterday too, so I'm not discriminating against you guys. Chemists often measure volumes in milliliters, right? Because it's convenient. That's good for the size of stuff that we deal with. But our concentrations are usually in moles per liter. And so, as you may be aware, we end up converting back and forth between liters and milliliters a lot, right? And it's time consuming. Every time you do a conversion, you have a chance for doing it wrong. either going in the wrong way or moving the decimal point the wrong number of places. Another thing is that the amounts in moles are often very small numbers, and we can't conveniently express them in decimal notation. So you'll get 0.00005. Well, all the zeros start to swim together, and you're like, you have to get your finger out and count them, and you feel like a first grader, or you have to put it in scientific notation. Using millimoles solves both of these problems, okay? So milli is the metric prefix meaning 10 to the minus 3, 1/1000th, right? So 1 millimole is 1/1000th, or 10 to the minus 3 moles. I think everybody's okay with that. So molarity, capital M, remember, is moles per liter. If I multiply the top by milli and the bottom by milli, have I changed anything? No, I haven't changed anything. Because what I could do is I could say, well, I'm just going to cancel the millis out. They cancel out, right? Still moles per liter. So that's all we're doing when we're using millimoles, is we're just thinking of molarity as millimoles per milliliter. And you can write it all out if you want to, but that gets tedious. Okay, so we're going to use millimoles. Consider the titration of 25 milliliters of 0.1 molar HCl with 0.1 molar sodium hydroxide. Find the volume of sodium hydroxide needed to reach the equivalence point. Now, some of you may be able to look at this and say, well, it's 25. Duh. Okay? Because these concentrations are equal to each other. And this is a 1-to-1 ratio. So it's going to take 25. But what if the numbers weren't so nice? Let's make sure we know how to do the calculation. This is stoichiometry. Yesterday someone asked, well, can you use M1V1 equals M2V2? Well, you can, and you can get the answer right sometimes. If this is a 1-to-1 ratio, that's going to work just fine. But I know that students like to do that, and so I'm probably going to put a question on the exam where it's not 1-to-1, and if you do M1V1 equals M2V2, you're going to get the wrong answer, right? It's just stoichiometry. So what I teach my 1A students is, here we have our balanced chemical equation. We're going to use that to organize these numbers, and write 25 milliliters under the HCl. And it says it's 0.1 molar. So that's moles per liter, right? And then I have 0.1 moles per liter sodium hydroxide. So I've taken all those numbers and I put them down. And then they're asking us to find the volume. So we're looking for the volume, and what would be the most convenient unit? Milliliters. So here's your review of stoichiometry. Grams to moles to grams. That's the starting point. There's always moles in the middle. There was a TV show called Malcolm in the Middle. Anybody remember that? Malcolm in the Middle? Well, for stoichiometry, it's moles in the middle. There's always moles in the middle. Grams to moles to grams doesn't always work because here we don't have any masses. So sometimes we have to change up the initial unit or the final unit. The moles to moles in the middle stay the same. So here, I can't write it there. We're going to have milliliters. And at the end, we're going to find milliliters. And in Chem 1A, what you probably did is you did milliliters to liters to moles to liters, and back to milliliters. We're not going to do that anymore. We're just going to go to millimoles. Millimoles to milliliters. So I'm going to start with the milliliters of the thing I know about, which is the HCl. So 25.0 milliliters HCl. And so this is going to guide my calculation. This is the path. I talk about Dora the Explorer, you know, she's out there, and who do you call when you don't know which way to go? The map, right? There will come a day when I won't be able to use that anymore because everyone will be too young and they won't know who Dora is. But I know that you guys still know who Dora is. And then the map comes out and says, oh, well, if we want to go to the snowy mountains, first we have to go through the scary forest and blah, 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 right? And then they chant this, 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 this. So this is Dora. Milliliters to millimoles to millimoles to milliliters. And that's just going to tell us exactly what to do. So there's 3 arrows here. That means I'm going to have 3 fractions. And why was her head shaped like that? So milliliters of HCl to millimoles of HCl to millimoles of NaOH to milliliters of NaOH. You see this? Milliliters to millimoles to millimoles to milliliters. It's the same thing. I need my units to cancel out. I need this unit to go away, so I'm going to divide by it over here. Milliliters of HCl. They cancel out. Bye-bye. I need millimoles of HCl to cancel out, so that I do that, and I do this. Dimensional analysis means you analyze the dimensions first, the units, and then you put the numbers in. So now that I've got all my units in place, the units are going to tell me where to put the numbers. I don't have to think about, well, am I supposed to multiply by the molarity or divide? Do I multiply by the moles of sodium hydroxide? It's all in here. I want millimoles of HCl per milliliter. Well, I didn't mean to draw a line through that. Let's get rid of that. It's 0.1 moles per liter, or 0.1 millimoles per milliliter, right? So it's 0.100 millimoles over 1 liter. This is the mole ratio from the balanced chemical equation. 1 mole of this to 1 mole of that. And then here at the end, millimoles are on the bottom and milliliters are on the top. Again, we can think of this as millimoles and milliliters. So I've got 0.100 millimoles per liter. 25 times 0.1 divided by 1 times 1 divided by 1 times 1 divided by 0.1 gives us. So there's your review of stoichiometry calculation. Okay, any questions? The good news is we're not going to do that particular calculation a lot, but we need to have an understanding of what the whole titration thing is about. So we're going to think about that same titration, 25 milliliters of 0.1 molar HCl, titrating with 0.1 molar sodium hydroxide. And we're going to look at what's the initial pH of the solution before we start the titration. So what do we have before we add any sodium hydroxide? We have 25 milliliters of 0.1 molar HCl. .100 molar HCl. What do we need to find the pH? The H plus concentration, right? Strong acid or weak acid? Strong, because it's one of the 6 and you memorize it. So this reacts completely, makes, if I have 1 mole of this, I get 1 mole of that and 1 mole of that. So 0.1 molar HCl then would correspond to 0.100 molar H plus, right? pH is the negative log of 0.100, which equals 1. Any questions? So on the graph, let me put a little red dot here. 0 milliliters of sodium hydroxide, the pH is 1. What about when we add 5 milliliters of sodium hydroxide? So this is where we're going to have to use one of those MICMA tables. We're going to have to do some stoichiometry before we can find the pH. So we're going to look at, well, what's being added? 5 milliliters of 0.1 molar. But this has to be done in moles or millimoles, not molarity. So how do we figure that out? Well, 5.00 milliliters times 0.100 moles per liter. Well, you can throw milli in there, right? And you're going to get 0.500 millimoles. No unit conversions. Volume in milliliters times the molarity gives you millimoles. So I'm adding 0.5 millimoles of hydroxide. How much acid do I have? I have 25 milliliters of 0.1. 25 milliliters times 0.100 molar is 2.50 millimoles. If we did this in moles, which is what the book does, we're going to have 0.000500 moles. And then all of this is more stuff to write, takes up more space, and the more stuff you have to write, the more opportunities you have to screw it up. That's, so, let's just avoid writing stuff as much as possible. So we're adding hydroxide, it's going to react with the acid. This isn't a buffer, but we've got acid, it's going to react with the acid. And so we look at these, and this one's smaller. We're going to assume that this reacts completely, giving us none of this, essentially. And 2.5 is going to go down by 0.5, and so we'll have 2 millimoles of H plus left. Okay? Now, we need to convert that to molarity, but the volume of the solution has changed. The volume has changed. So here's the millimoles of acid that we have left, and we need to divide by the new total volume, which isn't hard. You just have to remember to do it. How much did you start with? Start with 25. How much did you add? 5. I'll add those together. And so we're going to get 0.667 molar H plus. And then pH of that, negative log, 0.0667. .176. So the pH went up a little bit. Add sodium hydroxide, it should go up, right? Any questions? So today we're doing this with a strong acid and a strong base. The calculations are a little simpler because there's no equilibrium. Next week, we're going to do it with a weak acid or a weak base. So we'll be doing this part followed by an equilibrium calculation. So it's important to understand this so that when we add the rest of it, it's not just a big overwhelming thing. So let's add some more. I'm not going to do all of these. 10, 15, 20 milliliters. Pick one. 15. We're going to do the calculation for 15. So I'm adding hydroxide, and it's reacting with the H plus from my acid. What are the initial moles of hydroxide? So here, this is not that we added 5 and then an additional 10 and an additional 15. This is 15 total, right? We started at 5, then we went up to 10, and we added 5 more, and we got to 15. So we don't need to think about what happened before. We're just going to use the 15. We have 15 milliliters of 0.1 molar sodium hydroxide. So that's 1.50 millimoles. Isn't that easy? 1.50 millimoles of hydroxide. How much of the acid do we have? It's actually the same, because we haven't done anything to that. 2.5. Are you okay with that? Add 25 milliliters of 0.1 molar HCl. The amount of H plus is 25 milliliters times 0.1. I'm adding 15 milliliters of sodium hydroxide, 0.1 molar, 15 times 0.1, 1.5. Scoot those down there. So then the change. We're going to look at which one is smaller. That one's going to get all used up. Minus 1.50. Minus 1.50. And then the moles after, it's an A, is going to be 0 and 1. Right? I'm going to get rid of this guy down here now because we need the space. So to find the pH, I'm going to take the millimoles of acid and I have to convert that into a volume. A concentration. So I'm looking for H plus concentration. So I've got 1 millimole, and I'm going to divide by the total volume. We started with 15 milliliters. 25. And added 15. It's a good thing I took that nap. And I forgot to point this out on the previous slide, but because we're using millimoles here, we can use milliliters here, and they're just going to take care of themselves when we're going to get molarity. No unit conversions. None. It's beautiful. Just be willing to try it. So 1 divided by the quantity, 25 plus 15, gives me 0.025 molar H plus. And then the pH is a negative log of 0.025. One 1.60 to 1.60. So the calculations for the pH here are complicated by the fact that as we do the titration, the volume in the flask gets bigger, is constantly changing. That's why we have to look at moles here and not concentrations. So these are the values that they got for 10, 15, and 20, and they put those on the graph. Any questions? What about at the equivalence point? Well, my initial moles of sodium hydroxide are 25 times 0.1, 2.5 millimoles. And I've got 25 times 0.1 of the H plus. And we wouldn't really need to do this table, but I'm going to do it anyway. We end up with 0. We end up with approximately 0. You ever tried to take the log of 0? Calculator doesn't like it. This one says domain error. Like 1 divided by 0. Oh, divide by 0 error. That's more specific. You can't do it. So it's not actually 0. What we've done is we've neutralized it. It's pure water with sodium chloride in it. What's the concentration of hydrogen ion? The pH is 7. In pure water, these are equal to each other. So the hydrogen ion concentration is 1 times 10 to the minus 7, and the pH is 7. We had an acid, a strong acid, and we added strong base to completely neutralize. We end up with a neutral solution. Go figure, right? It's not acidic, it's not basic, it's neutral, because that's what we set out to do. So the pH is 7. Anytime you titrate a strong acid and a strong base, doesn't matter which one is in the burette, at the equivalence point, it's going to be 7. What we'll find out is it's not the case for weak acids and bases. So there's 7 right there. Any questions? No?
We want to know if you would drink it when it's 7.
Actually, yes, you could.
Yeah.
So if you were titrating hydrochloric acid and sodium hydroxide, you could drink it at the end point. It's salty water. Would it taste good? No. Should you do that? No. Because, it might have been contaminated with something, or maybe you mismeasured and it's not actually 7, right? There's all kinds of reasons not to do that. Okay, so what if we go past the equivalence point? We tried not to do this in Chem 1A. We wanted to stop at the equivalence point. Here, we're going to keep going and see what happens. So 30 milliliters of sodium hydroxide. Again, we make the MICMA table. So 30 milliliters times 0.1, we've got 3 millimoles of hydroxide and 2.5 millimoles of hydrogen ion. So now this is the limiting reactant. This one goes to 0, and this one is left. So now we have 0.5 millimoles of hydroxide left, but we want the pH. Well, first let's find the concentration of the hydroxide. So 0.50 millimoles, and we're dividing by the new total volume. 25 milliliters plus 30 milliliters. .0.0090909 goes on and on. Is it just like super simple and easy to find the pH from this? It's not super simple and easy. I mean, it's relatively simple and easy. But on the circle of pH, we're on opposite sides. So we need to do two calculations. Yeah. So what I think is easiest is to find the pOH first. Negative log of 0.0090909090. 0.9009. 2.04. And then the pH is going to equal 14 minus that. Because we learned that the other day. $11.9586. 11.96. And here we have a point that's very, very close to 12. Any questions? Bless you. And then we could keep going. I'm pretty sure you don't want to see another calculation, so I'm not going to do another one. But it's the same as the last one. You know, you've got your new volume of hydroxide and your old volume or old amounts. And so you find out how much hydroxide is left over, and then you find the molarity, and then you find the pOH, and then you find the pH. So this is the overall curve, pH curve for strong acid with a strong base. You're going to have your initial pH of the acid solution, and then before the equivalence point, you have an acidic solution. At the equivalence point, it's going to be pH neutral, and then afterwards, you're going to have a basic solution, and it'll keep getting more and more basic. If you titrate a strong base with a strong acid, if you switch them around, the curve is going to be essentially reversed. So you're starting with a strong base, you're going to start with a basic solution, and it's going to get gradually more acidic. It'll be 7 at the equivalence point, and then you'll have an acidic solution at the end. Okay, 50 milliliters of 0.2 molar sodium hydroxide is titrated with 0.2 molar nitric acid. Calculate the pH after the addition of 60 milliliters of nitric acid. This is the same calculation we were doing, but it's different things, right? And so would I ask you to do those repetitive calculations on an exam? Absolutely not. Would I ask you to do one of these? Yeah, I probably would. So what we should do is write the equation. Sodium hydroxide with nitric acid. And those are strong acid, strong base, and so we're going to get H2O and sodium nitrate. What we want to make sure is that we've got 1-to-1 here, okay? And we do. So we could make our little table. Here we're adding the acid. So we're adding the hydrogen ion, and that's going to react with the hydroxide that's already in the flask to make water. So we look at the moles initially present. Well, the sodium hydroxide, we have 0.2 molar and 50 mils, right? So 50 milliliters times 0.2 molar is what, 10 millimoles? So I have 10 millimoles of hydroxide, and I've added 60 milliliters of the nitric acid, 60 milliliters of the 0.2, it's going to be 12. Okay? You take the volume and you multiply by the molarity. If your volume is milliliters, then your result is millimoles, which is smaller. Well, usually 10 is smaller than 12. So that one's gonna get used up, and it'll use up an equal amount of that. So we'll have 2 millimoles of this, and essentially none of that. So now we need to find the concentration of what's left. Well, that one's gone. So the concentration of the H plus. That's going to be the millimoles divided by the new volume. 50 plus 60. Thankfully, we've got H plus there, not OH, so finding the pH is easier. .74. Any questions? 1.74. We are almost done, really, we are. So here we've got a strong acid in the flask, we've got a strong base in the burette. And they're asking us which mark on the burette would we have to add to get to an equivalence point. So, this is silly, but we're going to count the H pluses. 1, 2, 3, 4, 5, 6, 7. That means we need 7 hydroxides. 1, 2, 3, 4, 5, 6, 7. Next week.